So today we're going to talk about the voltage control oscillator, the VCO, within the noise toaster, analog synth. Here on the right you can see, actually it's the first half of the circuit, because here it's only showing the mixer and the exponential converter from voltage to current. The CV mixer is actually this part here, all this thing. And it's pretty basic. It's just, for instance, it's taking input from 3 different sources, so some control voltage. So for instance, it's taking it here on the left from the, so I think it's just a base frequency. This one in the middle is the LFO, so that's the one that we studied last time. So this is like the slow moving signal. And there's another potential signal coming from the attack release generator, I guess. So it's called AR gen mode depth. Okay, so you have 3 pots, you can control this, and you end up at the inverting input of the op-amp. And you can see here the feedback loop with that R11 here. And depending on what input you select, you get different amplification factor, because I'm sure the voltage levels are going to be different. So that's why you have different resistors here, R2, R14, R21, depending on the input. So it's just a very simple amplifier attenuator, because it's probably attenuating the signal. You have 2K over 75 or 100 or 36K, so it's not even an amplifier. And the output of that op-amp is here, and it's going into that exponential converter. So it's going to the base of the first transistor. So, I mean, the art of this thing is really this part. So this op-amp, which is going to control the current in that transistor, and then you have that second transistor, and at the collector current of the second transistor is basically your output. So that's your current, the output current. And that output current, it's gonna go into a ramp kind of setup, so that it can generate like a triangular wave, and the frequency of that waveform is going to depend on the current. So the idea behind all this really is that by changing the voltage here by 18 millivolts, so if you have 18 millivolts here, you're gonna get a current here. If you add another 18 millivolt to this voltage, so you add 36, this is going to double. So the current is going to double here, and it means that the frequency of the VCO is also going to double. If you add another 18, the frequency, I mean, the current is going to double, the frequency is going to double. So here it's, you add 18 millivolts, so it's like a linear change. And here you get a doubling, so it's like an exponential change. So that's why it's called an exponential converter. I'm not going to explain how this thing works on this schematics. I think it's better to go to the source, because this circuit, this sub-circuit, basically comes from, so if you look at this, it's coming from there. So it's coming from Bernie Hutchins Electronotes. I don't know if you're familiar with it, but it's very popular within the analog synth community, apparently. And it's volume S019. You can download it. And it's about log and exponential. Exponential is also known as anti-log circuits. So we're going to look into this, and because it's very well explained actually how it works. Okay, so this is that document, S019 Electronotes. As you can see, it's kind of old school. It's from 1981, but it's very well written. and very well explained. And the guy that's responsible for this is Bernie Hutchins, pretty well known in the world of analog synth with those Electronotes, and the website has tons of stuff too. Okay, anyway, I encourage you to read this thing because it's well explained. But anyway, let's go through a few things. So if you have your BJT transistor, you can express IC, which is the current going collector emitter, the collector emitter current, or also known as the collector current. And this is an NPN transistor. So IC is equal to I prime times exponential. So E is exponential Q VBE. So VBE is the usual voltage between the base and the emitter, divided by KB times T. And the important things to notice is that the collector current depends on VBE, but in an exponential way. So if VB changes a little bit, IC is going to change a lot. But the problem with this equation is you have that I prime, and I prime is temperature dependent. And there's also KB is the Boltzmann constant, but there's a T here, which is also a temperature. So this thing is very dependent on the temperature. So the IC is not going to be, if VB is constant, IC may not be a constant value. It may change because of the temperature. So that's a big problem. Yeah, so here he explains why this is pretty cool relationship, because if you were to try to do this with a linear component, like a resistor, to get this kind of range on the collector current, you would need to have a huge range as well on the voltage. And you would need, like, if you start at 10 volt, you would need to go to the micro volt to get the same range at the collector current level, which is impossible because the microvolt, as he's saying, is pretty much noise, so you cannot really control it. Okay, so then he's simplifying that equation. So now the equation is this one here. So IC is equal to I prime times exponential of VB divided by 26. So 26 millivolt and VB in millivolt as well. Okay, so let's not look into those. We don't care. Here it's important. Here, this passage here, this passage here, is telling you that basically that factor I prime, it can vary by about 7% per temperature degree, so centigrade or whatever. And there's also another factor that's also dependent on temperature, but it's only 0.33%. But you also have to worry about it, because even a small change like this, because this is frequency stuff, and the ear is very sensitive to change in frequency, even 0.33%, the typical person will notice if there's a change like that. Okay, so that it's very important to get rid of any possible variation due to temperature. Here is showing one way of doing it. So it's very a very simple way of doing it. But what we are interested in is this thing, this circuit, because it's exactly the same one that Ray Wilson uses in his noise toaster. It's the same thing. And I'm going to try to explain it as best as I can. Okay, so this is your voltage control. This is your control voltage, sorry. This is your control voltage. So usually the control voltage is going to be 1 volt per octave. That's the usual way of doing it. When you have a controller, a keyboard controller, that's what you expect. So you have 1 volt per octave. 1 volt per octave. And this op-amp, the only reason that we have this op-amp is so that it can transform this 1 volt per octave to a 18 millivolt per octave, which is exactly what we want, because it's gonna give us, if you have 18 millivolt per octave, it's gonna give us a doubling of the current. So if you increase V in by 18 millivolt, your current is going to double. And when the current is doubling, the frequency of the VCO is also doubling. So that's the reason why you have this guy here. Now I can focus now on the other part. Okay, so what we want to do, and I'll show that on why it's important because of the equations coming up next. What we want to have is a constant reference current going here into the collector of that first transistor. So we want this current here to be constant. And the way to achieve that is by using a op-amp here. So as you can see, the non-inverting input is at ground level, meaning that because we have a feedback loop here. So if you have a feedback loop, it means that the non-inverting input is going to be at the same voltage as the inverting input. So here we are also at 0. Okay, so here we have 0, and this is the supply voltage. So here is using 15 volts. So this is basically the positive battery. So this is 15 volts. This is 0 volts, and you have your resistor Ref. It means that the current in this branch, is equal to here, 15 divided by Ref. When you have an op-amp, the current here is only dependent on this resistor. Whatever you put in the feedback loop doesn't really matter, because what's going to happen is that the op-amp is going to output a voltage so that the current here remains constant and equal to 15 over Ref. Okay, so now we know that basically this thing is IRF is constant. Let's go to the equations. Remember that he was saying that the IC is equal to I prime times E exponential VBE over 26. So that's what we apply here. So here, so this is IC1. So this is this one. It's equal to IRF is equal to I prime times exponential of VBE. So VBE is equal to what for this T1? So VB is equal to V in, and VE is VE. So this is correct all here. So IC1 and IC2. So that's the second transistor. So IC2 follows the same rules. So you can use the same equation. So IC2 is equal to, again, I prime, assuming, so it's the same I prime, assuming that the two NPNs are matched. It's also assuming that the temperature they are experiencing is the same. So basically what you do is that you tie them together, or better, you get them in the same package so that you are sure that the temperature of the two transistors is going to be the same. So that's why you can put the same I prime. Otherwise, it wouldn't be the same I prime. So IC2 is equal to I prime times exponential of minus VE, because VB is probably ground, yes. So VB is ground. So minus VE divided by 26. So you can get rid of I prime, and you get IC2. So IC2 is equal to IC1 times exponential of minus V in over 26. And here you can clearly see that V in here, it's being exponentiated. So you can see that the collector here, the collector current here, is equal to some constant, which is IRF, times exponential of minus V in divided by 26. So the V in again is this guy, the one that varies by 18 millivolt. Let's carry on. Okay, here I should say that usually, and I think that's what happens in the noise toaster, you don't need this circuit here, because you have here the collector current that you're interested in. That's the one you want, that's your output. But here is putting a op-amp to transform that current into a voltage. And here is explaining the role of the various components. You can read it, but I pretty much went through it. So Okay, yeah, so what's important on that first op-amp is that is changing the sign of the control voltage. So it becomes negative. And why you want to do that? Because of this guy. IC2 IC2 is equal to IC1 times exponential, and you have the minus sign here. So if B in is negative, then you are on the positive side of the exponential curve. That's what you want. That's when you get the exponential behavior. And here is explaining that the resistor for that op amp is a special type so that you get rid of that 0.33% issue with the temperature. And then he's also saying something about, because there is something a little bit, okay, let's go back. Okay, so let's look at this thing. So if you look at the feedback loop is this guy. And you have the 2.2K resistor here, and this is just to limit the current. Okay, so it's kind of a classic to see that in the feedback loop. And this one is a bit more unusual. You have a 30 picofarad capacitor in parallel, and that one is a compensating capacitor. I'm not completely sure why it's needed, but apparently it's helping the op-amp maintaining the constant current, which is the same thing as saying that it's maintaining the virtual ground here. Okay, so this circuit that you see here, without this one and without this one, is exactly what you have in the noise toaster. It's exactly the same thing. The only difference is that here is using a real ground, but in the noise toaster is using a virtual ground at 4.5 volts. That's basically the only difference. And of course, the values of the resistor is a bit different. I think here is using 10K, and here is using 100 pico. But other than that, if you look at the schematics, it's exactly the same thing. But I think here it's much easier to understand what's going on. Okay, so this is the LTspice simulation of that exponential converter. And it's exactly the same as the one in the Electronotes. Yeah, so here you have that 15 volts battery supply. You have that RF. So RF needs to be pretty large. I put 1 meg. So you have your two transistors tied at the emitter. You have your op amp here, which is gonna make the current in this branch constant. So it's gonna be your I ref. You have your 2.2K resistor in the feedback loop, and you have your 30 picofarad capacitor in parallel. And this is the output. So the output is actually the, you can do it, the output is the current in there, or if you prefer the voltage here. I mean, they are both proportional, so you can have a look at any of them to see the effect of, so the effect of changing the, so X, what is X? Oh yeah, so that's my V in. Oh yeah. So this is the control voltage, that 18 millivolt business here. It's here. So it's at the base of that first transistor, T1. And what I did here is that I use stepping parameter values from -18. So you increase by 18 or you decrease by 18. So -18, -36, -54, -72, -90. As you can see, the difference between any two of those in sequence is 18 millivolts. So it's varying by the same amount. And the result, so the current here or the voltage here should double. It should double every time. So let's run this thing. Okay, so let's look. We can either look at the current, or you can look at the, let's look at the voltage. So the voltage is here. And so this is the first one, and this is, also this is the minus, so this is going to be the max. So this is minus 90 millivolts. And the first, this one is probably the magenta one, purpley one is probably the minus 18. Yeah. Okay, so this is minus 18, minus 36, minus 54, minus 72, minus 90 in millivolts. And as you can see, it's doubling every time. So we, for instance, if you look at this one, it goes from probably 60 to 120, then from 120 to 240, 45 maybe, and then it goes to probably around 490. So it does what it says it would do. So for every increase of, okay, let's go back. For every increase of 18 millivolt in that input voltage, you get a doubling of the voltage here, or the doubling of the current. And this current is going to be fed into the second part of that VCO. And what happened is that the current is going to charge a capacitor, and that capacitor is going to discharge as soon as the voltage reaches a certain value. And this is how you can control the frequency. So the current doubles, and as a side effect, the frequency doubles. And that's how you get the voltage control oscillator. So the frequency depends on that. The frequency depends on that V in, but it's doubling every time. All right, I think I'm going to stop here. I'll see you around. Bye.